Okay, today's lesson is the Law of Sines, section 5.5 from the book. Okay, without further ado, this is the Law of Sines. So we have this convention that the angles of a triangle will be labeled A, B, and C. A lot of times we use Greek letters for the angles, but now we're just going to use the capital A, B, and C. And then the lowercase letters are going to be the lengths of the sides of the triangle, and the lowercase side will be opposite the uppercase angle. Okay, so the picture says 1,000 words, I guess, and this is the law of sines for this triangle. If you take the sine of an angle divided by the opposite side length, that ratio is constant no matter which angle and side you choose. So sine A over A equals sine B over B equals sine C over C. The proof is not terribly important. I'm not going to ask you to know it, but then again, it's not terribly difficult. We have this formula for the area of a triangle. It's half the product of two sides times the sine of the included angle. And that's a formula probably you have on a note card. You should know it. So if you just apply this to all three angles, like angle B here, the area would be 1/2 A times C times sine of B. So you can compute the area of this triangle in any of these three ways, and then it turns out that when you multiply this equation right here by 2 divided by ABC, the 2's will cancel, and well, in short, you'll get this formula. Okay, so for what it was worth, there's the proof. Okay, so we'll look at some applications of the law of sines then. So this notation here, ASA and SAA, talks about getting two angles and an included side, or two angles and a non-included side. So in short, we're going to get two angles in the triangle and any one of the three sides. Okay, so here's an ASA example. So we've got two angles, 52 and 70, and we've got the included side, that is the side between those two angles. And our goal here is to find this other side of the triangle, the side X. I guess in the notation we were just looking at, we could have labeled this as little a because it's across from angle A, but the picture labels it X. Okay, so it's important to remember whenever you're given two angles of a triangle, the third one is essentially a freebie, right? You just have to remember that the angles add up to 180. So the angle C is going to be 180 minus 70 and minus 52. I'm not going to take chances trying to do that in my head. I'm just going to go ahead and get my computer to tell me that the third angle is 58 degrees. Okay, it was important to get that because in order to use the law of sines, we need to know the angle that's opposite the given side. So here we go. This says the sine of 52 divided by 26.7. So that ratio should equal the sine of, I looked at the wrong thing. This is the sine of 58. That's the angle across from 26.7. So that should equal the sine of 52 divided by X. Okay, so this equation will allow us to solve for the X. So let's see, I guess you could say that we would cross multiply. So X times sine of 58 is equal to 26.7 times the sine of 52. And so, and this is what I'm going to want you to do. I do want you to solve for this exactly and then get a decimal perhaps at the very end. So that would be our exact answer. And then because these are not known angles or special angles, 52 and 68, at this point you'd have to go to a calculator to get a final compact decimal. So I'll just get my machine to try to do it for us, and you can compare with your own calculator device. So x has length 24.8098. So I will tell you, and you certainly don't have to use this bit of advice, but if you want to, you can. This law of sine, it doesn't matter which of the terms you put on top and which on bottom. So we could also have, from the very start, written that 26.7 divided by sine of 58, that was going to be equal to x over sine of 52. And the only reason to do this, and again, it's just purely optional, is that it's slightly easier to solve for the x when you write down the relationship this way. Okay, so that was an angle side angle example, and now let's look at an angle side. Okay, so we've got two angles, but the side that we are given, the 17, is not the side between those two angles. So slightly different setup here. Okay, so we're going to try to find the x again. Right, so in order to use the law of sines, we need to know the angle that's across from x. That is, we need to know the angle C. And again, it's something you got to make sure you don't forget, is that third angle is always a freebie. So we get it from 180 minus 37.5 and also minus the 28.1. So that's the angle at C. And I will definitely not take chances this time. Get my machine to compute that that's 114 degrees there. Okay, so using the law of sines now, the sine of 114.4 over x is going to be the same as, let's see, we need the angle that's across from the known side, that's 37.5. So this would be sine of 37.5 divided by 17. Once again, we could have written those ratios upside down at the very start. It would have made it slightly quicker to solve for the x. But I'm going to do the x all in one go, though. So the cross multiply, we'll put 17 sine 114.4, and then we'll have to divide through by the sine of 37.5. Again, just practice with your calculator. You should verify that you're getting the same thing that I will get right here with my computer. The side length of x is 25. Yeah, so even if the decimal isn't requested or required in a problem statement, it's sometimes worth doing just to get a comparison. The 25 looks reasonable. The triangles aren't always drawn to perfect scale, but if this is side length 17, 25 looks like it could be reasonable for this. If x had turned out to be 470, you would have thought like, oh, something's wrong with this picture. Okay. So I'm going to put a timestamp in here. We are at just about 9 minutes. Okay, so that's one example where you get to use the law of sines, is when you know two angles and one of the other sides. And another place that you get to use the law of sines is when you know two sides and an angle that's opposite one of those sides. Okay, so I'll show you a couple of cases. So this is the picture. We've got two sides that are going to be given to us, and we know an angle that's opposite to one of the sides. Okay, so if we knew this angle over here, we'd be in a different situation. Beg your pardon. If we knew this angle, we'd be in a different situation. We would have an angle that wasn't opposite either of the sides. Okay, so if this is the setup and the side that's opposite the angle is bigger than the side that's adjacent to the angle, we say that this is an unambiguous case. There's only going to be one triangle that fills this bill, right? I'm going to show you a picture of the other situation, which is ambiguous. If the side opposite the angle is smaller. Oh, I don't have it drawn yet. Here we go. There it's drawn. Okay, so I just put it in a 45-degree angle. So this is some unknown side here, and we know the angle, and then we know the two next sides. Okay, so this is the ambiguous case. Okay, so the side across from the angle is now smaller than the side adjacent to the angle. And when that happens, it's called ambiguous because you might have two possible triangles. So this would be a case where you have two. I'm going to shorten this up just a little. Oh, I'm sorry, I'm doing it the wrong way. So 5 is less than 6. And what happens here is that we wind up with two possible triangles. This one and this one. Okay. Now, if the lengths are just set up right here like this, we might wind up with only one triangle. This is a situation where the opposite is actually the sine of the angle times the long hypotenuse. It actually forms a right triangle. Right? And then the last possible case here is that if this opposite side is much shorter than the adjacent side, then you're just dangling here in space and you get no triangles. So this again, this ambiguity comes when the opposite side is the smaller of the two sides. Okay, well here's the good news. We're only going to do the unambiguous case. That is, we will only be doing examples where the side opposite the angle is longer than the side that's adjacent. Okay, so our known angle here is 67. The opposite side is longer than the adjacent side. So there's only going to be one triangle that works, and we'll be able to find it. So what are the instructions here? The instructions are to first find sine of theta, and then find theta. Okay, so let's try that out. This sine of theta divided by 56.3. This should be the sine of 67 divided by 80.2. This was a situation where we didn't have to find the third angle, as it turned out. Okay, so the instructions are two-parter. The first is to find just sine theta. So we solve for it. Just multiply across, we get 56.3 sine 67 divided by 80.2. Okay. So I'm frequently going to ask for these two steps like this. The next step then would be to get a decimal for sine theta. This is to carry out the second part of the problem. So I guess you could try to enter all of this into your calculator at one go, but I think it's reasonable to try to get the decimal first, and then go to your calculator again and now get the inverse sine working for you. 619. And for me that's called, oh yeah, sorry about this. This will take a second. On my computer that's called the arcsine function. So again, just for you to check your own calculator. And my computer returns in radians, so to get degrees, I have to do this little conversion as well. Okay, so that angle theta in degrees, maybe I should put that, is 40.255. Okay, try another one, I guess. Yeah. So here we're well, again, we have two sides, and an angle opposite one of the sides. And this is the unambiguous, right? So opposite side 6.5 bigger than 3.4, which is the adjacent side to the angle. So unambiguous. I'm going to have trouble spelling that. Ambiguous. Made it. Okay. So we're asked to find the length of side AB, aka little c. The side opposite angle C should be labeled little c. Okay. Let's see. To get there, now we know this angle and an opposite side. Boy, this is going to take some work, because to use the law of sines to get the length of C, we need the angle C. Okay, but we only have one of the angles currently, so we don't get the third one free angle. So we're actually going to have to compute angle B first, and then that'll allow us to get angle C. At least that's the way I'm seeing how to do it. Let's try it. So sine of B divided by 3.4, it's going to be the sine of 80 divided by 6.5. Okay, so that's going to, oops, it looks funny. We can live with this, I think. So that's going to give me the sine of B is 3.5 sine of 80 divided by 6.5. A little work yet to do here. That's the decimal. And now we actually need to find the angle B itself by using, once again, the inverse sine function. Now this turned out to be a little involved. 0.51513, and then once again I'm going to have to switch it over to degrees. So hopefully you can just do this with the degree mode setting on your calculator to get that inverse sine function. So angle B is 31 degrees, and I think we can round to 31 degrees. So angle C will be 180 minus 80 minus 31. To be honest, I think I might have grabbed this problem out of a section where the instructions are to solve the triangle. And when you get instructions like that, it means find all of the remaining angles and sides, all that aren't given to you. So, all right, so now we have angle C, and that's going to allow us to get the length of AB. Okay, so sine of 69 divided by C, aka side length AB. And we can use either of the other two ratios now. I guess we'll just copy this one down. Okay, so 3 or 4 step process here, but I think we're on the final leg here. Solving for the C. And you can maybe do that in one extra step if you like. So hopefully something that's, by estimate, I would say it should be about 6.5, maybe a little less. Yeah, 6.16 looks about right for this picture. Okay. There are 2 other situations where we're given information that pins down, specifies exactly one triangle. It's when we're given 2 sides and an included angle, right? What we looked at so far was 2 sides and an angle that was not in between them. Right, so this is one additional case. And then a fourth case that we'll see is when we're given all 3 side lengths. That definitely pins down exactly one triangle. And we'll cover these two possibilities in the next section with the law of cosines. Okay, we're at 20 minutes. Let's see if we can wrap it up. Yeah, so this instructions here to solve the triangle. This means find all remaining angles and sides. Okay, so angle B, again, this is the free B angle, 180 minus 100 minus 30. I'm doing it this time, that's 50. And then the remaining sides. Okay, I'm going to use the notation that I kind of said we'd try to use here. Sine of 30 divided by side A. That should be, yeah, so the known side here is 2, so I have to go to this angle B, and we just figured that out. So it's a good thing that we figured that out first before trying for the sides. Okay, so we can solve for this. We get A is equal to twice sine 30 divided by sine 50. And as a decimal, comes out to be 1.3. And now, you need to be cautious about this. I've seen this happen before, especially when this angle right here is something that's close to 90. Students sometimes mistakenly try to get the third side using the Pythagorean theorem, which doesn't work because this isn't a 90-degree angle here. So to get the third side, that is side length C, we need to use law of sines again. So sine of C, which is 100 degrees, divided by the side length of C. Let's just copy this ratio down again. And we can solve now for the C. And we've now fully solved the triangle. Twice sine of 100 divided by sine of 50. These sine of 100 over sine 50, those don't cancel. It's not like sine of 2 or anything. It looks tempting when you see those, but they don't. And again, this looks pretty good given the picture. If this is side length 2, this could easily be 2.5. Okay. So lots of applications. Here is what I would say is kind of a complicated one, but it's one that a lot of your homework problems are based on. So you'll have this story problem given to you. So here the story problem is there's this observer sees a bird way up at the top of the flagpole here. The angle of the hill is known, and this angle alpha is known. I guess the alpha, somehow it doesn't match what I had written here. So I'm just paraphrasing the words problem here. Alpha is 9. The hill is at angle 50. This length C here is 110. So some stuff we're given. C is 110. And what do we want? What we're asked for is the distance from the observer to the bird who's up at the top of the flagpole. So we want side length B. Okay, do we know anything else? Not that I see. Okay, so what's critical in this, again, this is the picture that you'll get from the story problem. And what's important is that you're able to add in this little right triangle to the story problem on your own. Now the book happened to do it this time for you, but this is a skill or an idea that you need to use on several of the other word problems. Okay, once you put in this other little right triangle, then what happens is that you now know another angle in the red triangle. If this is 40 degrees, then angle ABC in the red triangle must be 140, because these two angles are going to add up to 180. Okay, so after adding the right triangle, and this is the important part, angle ABC is seen to be 180, and that's because it's just we're subtracting away from a straight line this time, not subtracting away from triangles. Okay, so that puts us in a good spot, because now we know two angles in the red triangle. We know the alpha and the angle at B. We know two angles of red triangle. Alpha equals 10, and the B angle equals 140. So again, the freebie, the C angle then must be 180 minus 140 minus 10, must be 30. Right? And in case we've lost it, also the C was given to be 110. So at this point, I think we've got enough ammo here to figure out side length B. Law of sines, LOS. It says the sine of B divided by side length B should be the sine of C divided by side length C. Okay, so, whoops, I meant to copy paste this and didn't get it. So this was 140. We were able to work out that angle by that little extra right triangle bit, and that allowed us to solve for angle C, and we were given that the side length C was 110. So finally we will get this critical bit of information. How far away is the darn bird? The bird is 110 sine of 140 divided by sine of 30. Now, sine of 30, we could compute that on our own as a half, but since we're going to the calculator for sine of 140, I don't expect you would do that. Okay, so the bird is 141 feet, meters, whatever units, meters away from the observer. All right, that's it for the law of sines.